Hello, so in this bonus video, we're going to look at calculating the transmission coefficient for tunneling through a barrier when the energy is less than the height of the potential barrier. So as we discussed in the main part of class, right, this is our potential energy that we're dealing with. And if we write down the general form of solutions to the time-independent Schrodinger equation in each of these three regions, we get something that's exponential in region 1, and region 3, that's complex exponential, rather. And then we have something that's real exponential in region 2. Okay. So the name of the game is as follows. We're going to think a little bit about the probability current and work out what the form of the transmission coefficient is going to be in terms of, it turns out, C and A. Then we're going to apply boundary conditions at 0 and A, and we're going to have to slog through quite a horrific bit of algebra with some hyperbolic trig identities to boot to get the final result. So Townsend sort of, states the boundary conditions and then sort of says in a problem that, after much algebra, well, there really is quite a bit of algebra, but it's not so bad, and it is, I think, worth doing this once for yourself so that you know that you can do it if you had to. All right, without further ado, let's dive in. So let's first think about the probability current. Okay. So in region 1, right, so where we have this form for the wave function, well, this is exactly what we did in the bonus video for Friday's class when we were looking at scattering from a potential energy step, right? There, right, we got Jx, we got h bar k over m um, times a modulus squared minus b modulus squared. Right? And if you want a reminder of what the probability current is, take a look back at that video, or look in section 2 point something, 2.5 or something like that, which is where Townsend works out what the probability current is. So that's just stealing the result from last time. We can sort of write down the answer in region 3, um, which is what we care about for transmission, because we want whatever penetrates out to here, by kind of staring at this and just writing down the answer. Notice that the wave function in region 3 is basically the same form as in region 1, except C become A the A has become a C and the B is equal to 0. So we can just steal the result here if we just send B to 0 and then replace the A with a C. We can straight away get C squared there. Now, if you want to, you can go in and plug this into the definition of the probability current, but you'll get exactly the same thing. So once again, right, the transmission coefficient is the ratio of the probability current here that's right-going to the ratio of the incident probability, right-going probability current here, which is this term. Right? So that leads, and again, the reason we have to do this is because plane wave states are not normalizable. So the transmission current is a ratio of J, let's call this J transmitted to J incident. And so that's going to be, right, H bar K over M times C modulus squared over H bar K over M times A squared, or as I claimed in class, modulus squared of c divided by modulus squared a. Okay, so that's our probability current. Now we just have to apply our boundary conditions. So the goal is going to be to solve for c over a. And now there are some hints as to sort of how to do this that that Townsend sort of drops a few crumbs. It's going to turn out, well, you can see from here that what we really want to see in terms of a, it will turn out to be slightly easier to get the ratio a over c first, but we'll focus on that. But our goal ultimately is to eliminate everything besides c and a. Okay. So now let's just write down the boundary conditions. Okay. So we know what the form of the wave function is from up here. Let's just for sake of writing this down, let's get our derivatives because we're going to need them. So d psi 1 dx. So here, so chain rule is going to pull down factors of ik. So this is going to give me ik, so I'll just factor that out. This gives me ik e to the ikx minus b e to the minus ikx. Okay. Let's go on to region 2, d psi 2 dx. Differentiating this is similar. It's going to pull down factors of kappa, and then flip the sign on this term, so we get a kappa f e to the kappa x minus g e to the minus kappa x. Good. And then finally for here, d psi 3 dx, this just pulls down an ik, and we get ik c e to the ik x. Okay, so we now just need to stitch this all together. So let's do the continuity of psi first. So at 0, at x equals 0, we have to stitch together psi 1 and psi 2. So that is going to, if I just plug in 0 into these two equations, so I get a e to the 0 is 1, I have a plus b, right, equals f plus g. So that's, let me call this equation 1. Okay. Okay, and now let's do the same thing at x equals a. We have to stitch together these two. Now it's a little messier because we have, the exponential terms don't just go to 1, but we get f e to the kappa a plus g e to the minus kappa a equals c e to the ika. Let's call that equation 2. So now we need to do continuity of the derivative, right? And so once again at 0, so we stitch together psi 1 and psi 2 here. So this time we get ik, plugging in 0 here, we get ik a minus b equals kappa f minus g. Right? Let's call that equation 3. And then at a, we do the same thing. We have a kappa f e to the kappa a minus g e to the minus kappa a equals ik c e to the I k a. Let's call that equation 4. So at this point, right, we already said that our goal is to get c in terms of a. It's going to be worth our while to strategize a little bit before we dive into the algebra. So one thing is, if we're mainly interested in the transmission coefficient, we really don't care about b for that purpose. So we should see if we can eliminate b. Is there a way to do that? Um, well, there is. If we look at these two equations, 1 and 3, uh, right, I can rearrange these and maybe like add them together to eliminate b. So let's just write this out actually. So plan, use 1 and 3 to eliminate b, right? And so that'll give us that'll give us a, f, and g. And we can use 2 and 4 also, right? We could try to solve for f in terms of, uh, we could try to eliminate g here and solve for f in terms of c to find f and g in terms of c. And I'll show you what I mean by that in a second. And then so we'll just have something that depends on a, f, and g. We can plug f and g in. That will give us a in terms of c. Here having a game plan does matter, I think, because there are so many steps. But okay. So let's start to carry this out. See if I can, okay, I can go, yeah, there we go. Okay, so I've got my 4 equations. So what do I mean by eliminating b? The strategy is often to like add these equations together or subtract them in some sort of clever way. So there are several ways I can do that. Um, Notice that if I were to take equation 1 and multiply it by ik, and I'd have ika plus ikb on the left, and then if I add that to equation 3, I have ika minus ikb on the left. I'd be able to just cancel out the ikb's. So that's what I'll do. So if I multiply 1 by ik, this gives me ik, and I'll just leave it factored, plus b equals fik f plus g. And then now if we just add 2, right? I add equation 2, and that gives me an ik. So sorry, equation 3. Oops. Equation 3 is the one I'm. Equation 3 is what I'm talking about here. Right, so I have an ika minus b, and I'll just rewrite it for clarity's sake. I have a kappa f minus g. Okay, so let's do that. And so I get 2 ika, the b's cancel, and then I get ik. Let's just keep the f's and the g's separate. I have ik plus kappa times f plus ik minus kappa times g. Okay. That's, let's call that equation 5. We might need to refer back to, we will need to refer back to it. Okay, so that's how we've eliminated b. Now we're going to do something similar, right? Because we want to get f to deal with f and g. So what we'll do this time is now look at equations, 2 and 4 over here. So if we do that, so let's see, what shall we do this time? I will this time, yeah, I'll multiply 2 by kappa. And that will give me now kappa f e to the kappa a plus g e to the minus kappa a, and then equals kappa c e to the ik a. And now, if I, so this is sort of 2. If I now, I'll just write down 4 again. And so this gives me f e to the kappa a minus g e to the minus kappa a equals ik c e to the ik a. Okay, now if I add these two equations, I'll be able to get f in terms of c. And if I, so let's do that first. So if I add them, what I end up with is, let's see, so I have 2 kappa, whoops, want to stick with black here, 2 kappa f e to the kappa a. These two terms cancel, and I get ik plus kappa times c e to the ik a. Now, so that's f, or basically f in terms of c, right? So let's actually let's finish this off and solve for f, right? So this gives me f equals ik plus kappa divided by 2 kappa, and let's just multiply e to the minus kappa a times, then that gives me c e to the ika. Okay, so we can similarly get g if we subtract these two equations. So I subtract these, the f's will cancel, and I'll have g minus minus g, which is a plus. So if I subtract these two, sort of scoops this on up, let's see, so that gives me, say the f terms cancel, so that gives me a 2 kappa g e to the minus kappa a equals kappa minus ik c e to the ik a. Okay. So once again, solving for g, this gives me now kappa minus ik divided by 2 kappa e to the positive kappa a c e to the ik a. All right, so now, right, let's just take this, let's take f and plug that in here, and then similarly we'll take this equation for g, so let's plug in, oops, you can't see that, we'll plug that in. That will leave us with an expression for a, where that only has a and c in it. All right, so let's carry on. So let's see, I'm gonna see, let's see, okay, so let's see, I don't think I can show you 5 all at once, so no, I'll just recopy 5. So 5 recopied gives me 2 ika, 2 ik a equals ik plus kappa f plus ik minus kappa g. So plugging in, this gives me 2 ik a equals ik plus kappa. My f is now here. So I get a factor of ik plus kappa, another factor of it squared, divided by 2 kappa e to the minus kappa a c e to the ika. Okay. And then now I have something that's quite similar. I have this ik minus kappa times this, which looks like ik minus kappa. I'm gonna actually get something to get it to look similar to this, where I have ik minus kappa quantity squared by just factoring out a minus sign here. So I'll just write this as minus ik minus kappa, the quantity squared, over to kappa e to the kappa a, ce to the ika. Okay, this is a little messy, but we're getting somewhere. Um, so, yeah, so just convince yourself that this is legal, that, yeah, I just pulled out a minus sign. Everything, so far, so good. Okay, so now it's going to be a matter of simplifying this. I think I can pull this page away. Okay, so, what I'm going to do is just sort of guided by knowing how this goes. I'm going to ultimately solve for A over C, because that turns out to be a little bit easier to deal with. So notice we've got something, right? We've got a C in both terms here, so I can pull that out. Similarly, I can divide both sides of this by 2ik. And we have some common factors, right? We have a common e to the ika. We also have common factors of 2 kappa. So let's just do that, and then we'll simplify. So we get an a over c. I'll pull out all the stuff that's in front. So the common stuff is e to the ika upstairs. Downstairs we have 2 kappa, but I'm also going to divide by 2ik. So that gives me a 4ik kappa. And then we already pulled out the c and divided it over. So now if I put in big square brackets, we have now ik plus kappa quantity squared. What's left is the e to the minus kappa a. And then in this term, what's left is minus ik minus kappa squared e to the positive kappa a. Okay, so this is starting to get a little bit better. So Townsend gives us some hints so he gives you some hints as to how to simplify this. He ends up with an a over c in terms of hyperbolic sine and cosine. So we'll go with sort of his root here. What is going to be helpful is to now use some identities for hyperbolic sine and cosine. I like to think of them as sort of defined in terms of exponential functions. You can think about them geometrically as well in terms of like a unit hyperbola, although that's probably less, that may not really be more intuitive. The circle definition for like regular trig functions makes I think good sense, but we'll just write down the hyperbolic trig function definitions. So hyperbolic, so this I think is, in my opinion, is highly non-obvious. So you know, don't feel like you know if you don't like if it doesn't, oh, it's a hyperbolic sine or cosine, that something's wrong with you, because it's not. There isn't. So the way we define hyperbolic sine of x, sinh x, is as e to the kappa a minus e to the minus kappa a over 2. And the hyperbolic cosine, or cos x, goes like e to the kappa a plus e to the minus kappa a over 2. sort of notice how similar these are to like the expressions for sine x and cosine x in terms of e to the I theta and e to the minus I theta. Uh, so, um, so yeah, just to note that. Well, we can already kind of get that we might have some stuff like that here if we multiply out all of the stuff here. So let's go and do that. So if we multiply out, this gives us a over c equals e to the ika over 4ik kappa. Okay, so let's just multiply this. We have, so squaring this term, that gives me ik squared, gives me a minus k squared, plus 2ik kappa for my cross term, plus kappa squared, the whole thing times e to the minus kappa a. Then here I have minus, okay, let's multiply this out. I have minus minus k squared again. The only thing that's different is the cross term. This time I have a minus 2ik kappa plus k kappa squared times e to the kappa a. Okay. So let's so notice, right, we have, let's look carefully, right? We notice that here we have minus k squared and I have plus k squared times e. So let's sort of combine things where we can and compare, right? So these two middle terms have the same algebraic sign. We have two minuses. Two minuses here give me a plus. And here again, this term is positive, this term is negative. So we'll just group those together. Okay, so that gives me e to the ika, oops, okay, little a. Whoa, what happened there? Yeah, I miswrote this. That should be a lowercase a. Yeah, that should be a lowercase a. Dumb mistake on my part. E to the ika over 4ik kappa. Okay, let's do this. Let's start over here. So I have a k squared here, and then a minus kappa squared e to the kappa a. So I'm just gonna mark the terms that I've dealt with a little twiddle so that I don't like overcount these, and make sure I get all of them. And then we have here, so we have so I'm going to do a minus here. I have a minus k squared, but this is up here is a positive kappa squared, so I'll have minus kappa squared there. So minus minus will be a plus e to the minus kappa a. And then I'll have, so that, let's twiddle those out. And yeah, the twiddle strategy I find to be helpful when doing algebra with lots of terms to help me keep track of them. And then so now we have, right, so now we have a 2ik kappa e to the kappa a, 2ik kappa e to the minus kappa a, so we have plus 2ik kappa e to the kappa a plus e to the minus kappa a, and that takes care of these last two terms. Okay, so I think you can see where we might be going here. So let me just do a little bit more factoring. I'm going to now factor this common term k squared minus kappa squared out of here to give me, so still have all this stuff in front for ik kappa. So I have k squared minus kappa squared, e to the kappa a minus e to the minus kappa a plus 2ik kappa e to the kappa a plus e to the minus kappa a. Okay, so this is good now because this is now 2 sinh kappa a, and this is 2 cos kappa a. So let's do that. So write in terms of trig functions. See what we got here. Okay, let's see. I think you can, so you can see the next line of algebra. So this gives me e to the ika over 4ik kappa. So we have k squared minus kappa squared. We have now 2 from the definition of sinh. We have 2 sinh kappa a. And then we have here 2ik kappa times 2 cos kappa a. Okay, so so let me slide this up. We can now simplify this a little bit. So notice that if I pull out the factors of 2, we end up with a over c is going to be e to the ik a. It's going to cancel a 2 down here, 2ik kappa times k squared minus kappa squared sinh kappa a plus 2ik kappa cos kappa a. Okay, so there, that gets us something that's a little better looking. But we still have work to do, and namely, what we'll now do is work out the transmission coefficient, or 1 over it. So now find 1 over my transmission coefficient, which is right. So that's going to be a modulo squared over c modulo squared. But I can do that by just taking a over c times a star over c star, right? And that will give us a modulo squared over c modulo squared. So we at this point need to just crank on this. So let's just let's just think. Let's be strategic again, so that we don't drive ourselves um, too too nuts. So rather than write out this whole thing twice, notice that if I notice that okay, so the constants out front aren't so bad to deal with, right? Because they're not hard to complex conjugate. The messier thing is multiplying this square bracket thing by its complex conjugate. But notice that this is a real number, right? And then this is I times, 2k kappa cos kappa a is also a real number. So this is really like quite literally a plus bi times a minus bi. And what I think you know is that if you complex conjugate that, multiply by, when you multiply a plus bi by its complex conjugate, the cross terms vanish. So we won't bother with that. And so let's just do the prefactor. So we have e to the ika times e to the minus ika gives me a 1 upstairs. Downstairs I have 2I times minus I, which is going to, so we'll have a factor of 4 for the 2. I times minus I gives me positive 1, I have a k squared kappa squared there. Okay, so this term squared is going to give me k squared minus kappa squared, so we've got k straight, the quantity squared, sinh squared kappa a. Okay. Cross terms vanish. Now I'm going to have to multiply this by its complex conjugate. So I have a 4. I have an I times minus I is a 1. K squared kappa squared cosh squared kappa a. Okay. Now Townsend claims that this simplifies, which it does. We just have to manipulate this even more. At this point, what it's gonna turn out to behoove us to do is to square this piece here. So if I multiply that out, it doesn't maybe look like it helps, but let's do that. So that gives me a k squared, k to the 4th, sorry, k to the 4th minus 2k squared kappa squared minus 2k squared kappa squared plus kappa to the 4th sinh squared kappa a plus 4k squared kappa squared cosh squared kappa a. Here's the other sort of trick that ends up getting pulled here, namely a hyperbolic trig identity. So it turns out, just like there's a Pythagorean trig identity, that cosine squared x plus sine squared x equals 1. So there is a hyperbolic cosine and sine identity, which looks like this. And it goes like cosh squared x minus sinh squared equals 1. You can go and prove this if you want by plugging in the definitions in terms of exponential functions. But let's just sort of take this on faith. You can look it up, you can prove it for yourself, or look up the internet or a math handbook if you wish. But if we look at this, right, notice that we nearly have something that goes like cosh squared kappa a. If I could get this in the right form, I could sort of get the coshes to go away. So namely, what do I mean? So let's just do that. So I have a 4k squared kappa squared here. And then I'm just going to have to not change anything. So let me just start. Right, a kappa k to the 4th minus 2k squared kappa squared plus kappa to the 4th sinh squared kappa a. And then what I'm going to want to do is I'm going to write this as plus 4k squared kappa squared cosh squared kappa a. To use this identity, I want a minus 4k squared kappa squared sinh squared kappa a. But I can't just add a term. I have to actually sort of not change my equation, so I'm just going to add 4k squared kappa squared sinh squared kappa a. Okay, so take a moment to stare at that and convince yourself that this is legal. But, right, notice that this stuff now simplifies via this identity. Moreover, I can simplify the right. I have this, I can combine those two terms. And so if I do that, I have 1 over 4k squared kappa squared. So minus 2 plus 4, minus 2 plus 4 gives me plus 2. And this gives me k to the fourth plus 2 k squared kappa squared plus kappa to the fourth sinh squared kappa a. And then by identity, I have plus 4k squared kappa squared times 1. Almost done. Okay, so almost there. So now I can bring, so notice that this now factors, oops, I'm going to use this for highlighting. So this term factors, and if I multiply this in, that cancels that. So this now means that with further simplification, let's see, I get 1 over t equals, pull this in. Yeah, I don't need to anymore. So this thing up here factors into k squared plus kappa squared, quantity squared. Right, let's check that, right, k to the fourth, 2k squared kappa squared plus kappa to the fourth. And I'll pull this in here to give me 4k squared kappa squared times sinh squared kappa a plus 1. So we are finally ready to write down the answer for t, which is what Townsend shows, and then you can take the limit of large kappa a to get the result that the transmission coefficient really does go like e to the minus 2 kappa a. So I'll just write this as sort of this whole thing in brackets to the minus 1. So we get, right, we have k squared plus kappa squared over 4k squared kappa squared sinh squared kappa a plus 1, the whole thing to the minus 1, and the Willikers were finally done. So, all right, thanks for watching.